this lecture, we're gonna study about time stepping. In particular, we're gonna look at uh, how we can achieve not just linear but also non-linear time stepping in PETSc. So, like everything else, time stepping is also encoded inside an object, a time stepping object. And as you can imagine, there's a host of algorithms. But what really do we mean by time stepping? So, by time stepping, we refer to marching an equation in time. So, it could be for an ordinary differential equation or a partial differential equation which has an unsteady term, and so on. So, basically, it can happen for both ordinary and partial differential equations. And so, if you have an ordinary differential equation of the form dy dt is some g of t comma y, right, where um, g is a set of functions. So I mean, y is a vector y1, y2, y3 and so on till say yn. So dy y1 dt is some g1 of t y1, y2 and so on. Dy y2 dt is some function of t y1, y2 and so on. And so obviously you can sort of assemble all this in the form of this vector equation, right? So then how do you actually achieve time stepping? I mean, there are various algorithms that exist. So algorithms can be broken up into single step algorithms or multi-step algorithms. So single step algorithms are usually much faster because they involve only maybe one set of function evaluations. Multi-step methods will involve usually function evaluations which will have multiple intermediate steps, or it may draw upon multiple time steps at a time, so that requires more computation. So single time step, so let us look at the simplest one, that is the Euler time stepping, so forward difference. So we can say y at n minus y, I mean, let's write it in a subscript form. So y at n minus y at n minus 1 upon delta t is g's of tn minus 1 and yn minus 1. So this is how you would write forward difference approximation for y. And you can obviously integrate this, I mean not integrate this, but easily step this in time. But this method has order delta t truncation error because this, as you can imagine, is a Taylor series expansion about y n minus 1. Similarly, you can have a backward difference method where instead of sort of going from n minus 1 to n, you can also write everything in terms of n, but there will be a prime difference. And I mean, you've most likely gone through this in your first year or whenever you have come across this. This will instead be g of tn and yn, and this usually culminates in the form of a linear system in yn. Okay, this thing is usually an explicit time stepping, so there's no matrix inversion as such. Well, apart from these methods, both of these methods suffer from order delta t truncation error, but We can also have the higher order methods, and the most famous higher order method is called as the Runge-Kutta methods. And I sincerely apologize for uh, incorrect pronunciation of the name. I'm not sure what this is called. I'm pretty sure it's called Runge. Okay, I'm not sure about that anymore. But anyway, doesn't matter what you call them. We call them the RK methods in short, and they are widely used. Okay, so there are various RK methods. There are Rk4 methods, which is order delta t square accurate. This the very famous Rk4, which is fourth order accurate. And there are other higher order methods as well. You can actually construct various methods as you go. So let me write down the second order Rk4. So suppose you have the information about y at the n minus 1th step at tn minus 1th time, and your objective is to time step from this to y at n, which is at t at n. So we declare an intermediate time y cap, right? So let y cap be equal to y at n minus 1 plus h times g's of tn minus 1 yn minus 1, where h is the time stepping, is essentially delta t. We've borrowed the same literature from spatial derivatives over here. So far it shouldn't create any confusion at all. And so essentially you're writing at an intermediate step. You're sort of doing a partial step towards the final goal. So this is that partial step. Okay, so beyond this we have yn will be equal to this intermediate value y hat plus h by 2 g's of tn minus 1 yn minus 1 plus h by 2 g's of tn y hat. Okay, so it's like a partial step. You first evaluate this, so this is that first step, and then you sort of take an average of the evaluation at this step and this step, and you take an average and then you perform the final time stepping. Okay, so this you go in two steps, and this is order delta t square accurate. The truncation order is of the order of delta t square, and you can easily prove this. I have given the form over here. You just do a back calculation using the Taylor series. The most famous form, that is the Rk4, which is the workhorse of solving ordinary differential equations, because it's quite robust and it gives us a great deal of accuracy with a very few number of computations. So the Rk4 method may be summarized as going from tn minus 1 yn minus 1 to tn yn in multiple steps. So the first step is to write k1 is equal to f of tn minus 1 yn minus 1. Then you can write k2 is equal to f of tn minus 1 plus h upon 2 yn minus 1 plus k1 times h upon 2. k3 is f of tn plus h upon tn minus 1 plus h upon 2 plus rather comma yn minus 1 plus h upon 2 k2 k3 sorry k4 will be f of tn comma yn minus 1 plus h times k3. And finally, after finding out these four intermediate steps, so this k1, k2, k3, k4, you finally write yn is equal to 1/6 yn minus 1 plus 1/3, sorry, not 1/6 yk minus 1, but this will be 1/6 k1 plus 1/3 k2 plus 1/3 k3 plus 1/6 k4 times h plus yn minus 1. Okay, so this is how you find out using four intermediate steps what the Runge-Kutta terms will be. So apart from these Runge-Kutta methods, there's also multi-step methods like the very famous second order backward differentiation formula, and you will find many of these things in commercial solvers like MATLAB. Not, I mean, you'll find this in MATLAB as well, but in COMSOL, Fluent, and all these things as well. So the BDF solver. So y at n will be equal to 4/3 y at n minus 1 minus 1/3 y at n minus 2 plus 2/3 times h times g's of tn comma yn. Okay, so this is order delta t square, so it's a multi-step method. Okay, so there can also be various time stepping methods which make partial use of such kinds of backward differentiation formulae and forward stepping. So typically we have to remember that implicit methods require more time because you have to in fact solve for an algebraic system, whereas explicit methods do not suffer such a kind of drawback. So now let us proceed to solve a very simple ordinary differential equation with the help of the PETSc time stepping. So let us first write down a governing equation that we intend to solve. So dy dt is equal to a times y plus f of t, where a is equal to 0 1 minus 1 0, f is equal to 0 comma t. So this is a driven term. So what do we have? dy0 dt is equal to y1 plus 0 and dy1 dt is equal to minus y0 plus t. So these are the two equations, and yeah, so let's see how we can solve this using PETSc. But before that, let me just point out that y0 is equal to t minus sine t and y1 is equal to 1 minus cos t. They are solutions and we can easily verify this. So dy0 dt is going to be 1 minus cos t, which is equal to y1. dy1 dt is going to be simply equal to sine t. So minus of y0 is going to be minus t plus sine t. So minus t plus sine t plus t, so the t cancels out and you get this. So this is what the solution is, and it will be useful for us because then we can compare whatever we obtain using PETSc numerically we can easily compare that. All right, so let's proceed towards writing the program. So let me create a new file. All right, so first things first, we must create a time step object, a time stepping object. And so let us go line by line. So the first thing we will do, hash include PETSc.h. Let me save this file. So let me save it as odts. Oops, I forgot to declare the extension of the file as .c. All right, so we've declared it as a .c file, hash include PETSc.h. Then let us write the main. So int main arg int argc char star star arg v return PETSc finalize. All right, so over here we're going to define the number of equations that we're going to solve. So int n equal to 2, and actually because n is not going to change, or rather we don't want n to be changed, we can declare it always as a const int 2. Alright, we're gonna need the number of steps that we want to integrate the equation. So int n steps. We also are going to need the initial time. So double t0 equal to 0.0, tf is equal to 10.0, the final time. This has to be a comma. And finally, the time stepping variable, that the dt is going to be 0.01. We are also going to need a variable to store the error between the analytical solution and the numerical solution find out using time stepping. So we're going to declare the error. So we abs error. Okay, so now apart from this, we're going to need a vector which is going to sort of keep on updating depending on the time stepping, and we're going to need a vector which will store the exact sort of values that we have from the analytical solution, just to make a comparison on how everything looks like. All right, so we're gonna need vec y exact, and apart from this we're gonna need a time stepping object. So ts. So this is the time stepping object. All right, so with the help of this we can perform the PETSc initialize. So in order to have a PETSc initialize, we will need certain arguments. So let me borrow that from one of our previous code. And the reason why we can borrow it, because nothing really changes across the different programs in this particular line at least. And instead of having a help string that solve the reaction diffusion system, we will say that it's to solve an ODE. Alright, so we've initialized PETSc. Now let us focus on creating the vectors. So we will do vec create. So this will be PETSc com world, and let us pass the address of the y array. This has to be small y. So essentially we are creating the vector y, and using various processes that we may or may not use. Then we will go through the usual grind. So it's going to be vec set sizes, then it's going to have y comma PETSc decide, and finally you will say you will pass the address of y. So with this we have done. So in set sizes we have to tell the number of elements, so it will be simply capital N, that is two number of elements. I mean, I could have hard coded it as 2, but still we like to maintain the modularity, so nothing to worry about. Finally we write vec set from options y, so that when you pass command line arguments in running the C program, you may pass some additional flags to specify either the solver or the Jacobian or the coloring of the Jacobian, so many things. And that is why this line is quite important to accept command line arguments. Finally, we have vec duplicate y comma the address of y exact. Alright, so we are sort of creating this variable and making a duplicate and calling it y exact. So finally we will construct whatever is going to be there in y exact and put it in y exact. We're gonna do the time stepping and save it in y, and finally we're gonna take a error between y and y exact and find out what how the function progresses. So far we have created the two vectors. Now we're gonna create the time stepping object. So ts create PETSc world, and we must pass the address of the time stepping object, and this is the same as dmda or ksp or anything. Okay, usually all the objects in PETSc have that similar calling sequence. Once we've created, we must set from options. So ts set from options, and we will pass the time stepping object, and we're gonna actually ts set options will come much later. So in this sequence we must first also specify what is the problem kind. So we will do ts set problem type ts nonlinear. So this is just to make use of any flexibility that we may need later on to make the program non-linear rather than having simply a linear program. But the linear program will run much faster than this. But anyway, we don't mind it so much. After this, we must do ts set RHS function, and this is the RHS function in the time stepping. This entire thing which we call as g is of y comma t, so that's the entire function. So in this case we will write down a user defined function which will be used to sort of make the function callback. So we have ts comma null comma form RHS comma null. So with the help of this, you're telling the time stepping object that whatever you're going to do, the right hand side callback has to be through the function which is called as form RHS. It can be any name you want. In this particular case, it's form RHS. Then we're going to set the TS type. So TS type, and the default will be the Runge-Kutta integrator. So TS comma TSRK. Okay, so TSRK is the Runge-Kutta time stepper. So once these 4 lines are done, you have created the time stepping object in which the problem type is considered to be nonlinear despite being linear in this case. After that, you're gonna declare the callback to the function when it tries to evaluate the right hand side. Now we're gonna set the time. So ts set time ts comma to. So this is to set the initial time. Then what do we have? ts set problem. We've already set the problem type. So set the initial time. After that, we're gonna set the max time. So ts set max time ts comma tf. Then we're gonna define the dt that we want to output the data at. So ts set time step ts comma dt. And finally, we want to match the final time step. So we must do an additional function call, and it is called as ts set exact final time ts comma ts extract, no, not extract, exact final time match step. Okay, so let me quickly open the function reference. So ts exact final time, so it determines whether to adapt the final time step to match the final step or just to return whatever final time you have. But it is good to have exact final time match step. Okay, so using this, it will sort of balance the final step. All right, so once this is done, we have to do a ts set from options, and the reason why we do this is to allow for user to pass modifiers or arguments to the time stepping object through the command line. Okay, if you not do this, it will not take form. Okay, so that takes care of this. So now we are yet to define what the form RHS function is going to be. But even before that, we know that because we have declared so many variables, we also have to remove a bunch of variables or destroy a bunch of variables. So we will say vec destroy ampersand of y, that is the address of y, vec destroy ampersand of y exact. Then you have ts destroy, much in line to the vec destroy, mat destroy and all that thing. So here we have to pass the address of the time stepper. Okay, finally, yeah, that's pretty much it. So far what we have done is created the vector, created the exact vector, created the problem, and the time stepper kind is in this case the Runge-Kutta. Then we have defined the times over which the integration has to occur. Okay, so it's going from t0 to tf in steps of dt. That is what is going on. So with this in mind, how can we proceed? So we must define the callbacks, and yeah, so let's see how we can proceed from there. So first of all, let us definitely define what the callbacks will be. Otherwise, without that, we will have no function evaluations. So we will write a function. So PETSc error code. So this is the return type. So form RHS ts comma double t. So that's the time, the y vector, and the G vector will be needed to populate it later on, and any user defined context. So y star ctx. So that's some user defined so application user context. So depending on what you are defining the structure as, you're going to pass this. Later on you can cast it, and we've seen this in one of the previous lectures as well. So in order to form the RHS, we are passing it the y vector, the time, and the g vector. So we must first convert this PETSc vec object into a C type array object. So the way to do it is to declare arrays. So because the vector y is not going to change, so cons double star ay, we will need a double star ag. So these are the auxiliary arrays. After this, we have to first set the array from the vector, then afterwards you have to unset. So we have done this plenty of times before. So vec get array read. For the case of y, it is going to be an array read. So it's going to be y comma the address of auxiliary y. Similarly, we can do vec get array, and we can pass g and the auxiliary function to g. Then we can simply say ag0 is something, ag1 is something, and then we can restore. So vec restore array read, we're gonna do y and ampersand of ay, and similarly we're gonna do a vec restore array g comma ampersand of ag. So ag0 is in this case simply going to be y1, and this is going to be minus y0 plus t. So let's proceed to write that down, nothing wrong. So ay1, and this will be minus ay0 plus t. So once this is successful, we can simply return a 0 to say everything is running fine. Alright, so now we've defined the callback function, which the time stepper will evaluate when doing the time integration, and more importantly, it follows the similar way of declaring things as we have done in the previous lectures pertaining to anything which makes use of such kinds of PETSc vectors. We have to first convert it into C vector, then convert it back into a PETSc vector. Okay, so let's continue. Not over here, this is the function. We have to go back to main. So what we have done is we have set from options, and now we must actually solve the actual thing. So let us do ts get time, the time stepping object and the initial time, set exact t0 y0, well, because there is no y0, is simply going to be y, because we have not yet done any time integration. So it y is so we have actually not defined what the initial condition is as well. Okay, but we are asking, okay, so we are asking the function set exact to take t0 and define what y will be. So this function helps in setting the initial condition. Alright, so set exact. Then once we have the initial guess, right, not the initial guess but the initial condition, then we can simply do ts solve ts comma y. So now the time stepper is going to update each value of y until it reaches the final step. Alright, and the final steps are sort of uh, fixed using this set of code. Not the final step, but all the time stepping dts and the final time are set using that. So at the end of this code, we should have the numerical solution in the variable y. Alright. So now what we can do is we can proceed and simply find out the error. Okay. So let us find out what the exact final time is. In case it doesn't match the final step, rather match the final time, we can actually fetch what the final step is going to be. So the function is ts get time ts, and you have to return so you have to pass the final time step variable. So now this will be the exact solution, not the exact solution but the exact time at the end of the solver. So this fetches exact time at the end of the solver. Alright, so once we have the time, we can actually find out the exact solution at the final time. Okay, so we can set the exact solution at the final time. So what is the exact solution? So set from not set from, so set exact tf comma y, rather y exact, we don't want to overwrite y. Okay, so now that we have y exact as the solution, exact solution, which is this, we can compare it with the approximate solution using the time stepping. Actually, over here when we are setting the initial condition, this is where we set the initial condition. The reason why this works is we know the analytical solution, and so we can set the initial condition simply by setting t naught into this expression. That is why this works. Otherwise, in general, you would have to specify clearly what the initial condition is supposed to be. Okay, but in this case, because it's simply this analytical solution with t replaced by 0. So now we have the exact solution. So now we, as usual, we'll find out the error using vec ax plus p ax plus y. So let's do that. So vec ax plus y comma minus 1 comma y exact. All right. So then we simply do a norm. So vec norm y comma norm infinity comma and pass the handle for the error. So we have abs error. All right. So with the help of this, we have the error. We will then destroy the variables which are not in use and finalize the program. So now all we need to do is make a function definition for set exact. Okay. So let's go ahead and do that. So the return value will obviously be equal to PETSc error code set exact double t vec y. Then we have to create the auxiliary array double star ay vec get array y comma ampersand ay. So we are passing the address of ay. We have to eventually do vec restore array y comma ampersand ay. So these are the things you need to do. And once you have extracted the PETSc vector y into the C array ay, we can find out the exact solution estimate. not the estimate but the exact solution, we can replace it by the exact solution expression. So in that case, ay0 will be t minus sine of t, and ay1 will be equal to 1.0 minus cosine of t. And if the program is successful, you return, what do you return? A big zero. It's quite contradictory if everything runs successfully. Okay, so that's the entire code. um, let me run through it once again. In fact, let me compile it first. So let me modify the make file to create a new target. Okay, so let me copy this. So instead of the reaction diffusion, control H, you replace it by ODETS. So then you do replace. All right. So let's save it. Let me launch the Ubuntu app. And after that, I have to navigate all the way to cd mnt c users admin dropbox tsc, then make odts, and let's see whether we have some errors or not. Okay, so I think we have missed a semicolon somewhere. So don't have to worry too much about this. Okay, so there's a semicolon missing over here. What else? In fact, let me redo this. There appears to be an error pertaining to semicolon once again. So the function name I've put incorrectly, so it's ts set type. Okay, so I've saved it. Let me make it. Okay, so we have are a bunch of warnings. But there are some errors. So vec set size, and it's incorrect because the function is vec set sizes, and ts set from options is actually, the s should be capital. So these are some silly mistakes that happen if you try to code too quickly, but anyway, it just goes to show that you have to be super careful. Okay. So the only warning is the n steps is unused. In fact, why don't we make use of n steps? What we can do is, once the solver is done, we can say ts get step number from the time stepping object and put it into n steps. So at the end of it all, what we can do is, before destroying everything, we can print. So we can do a PETSc printf PETSc world. So final time percentage 1.4f slash t, number of steps, so n steps percentage d, because it's going to be an integer, slash n. So we can simply go over here and say ts comma n steps, and let us additionally write down error percentage g, and this will be simply y. No, not y, it will be error yeah, because not error, I mean it has to be apps error. So what we're doing is finding out the ax plus y, that is y minus y exact over here, and then finding the infinity norm over here and assigning it to ABS ERR, which we are printing over here. Let's not forget to put a semicolon over here. Alright, so now we can compile this, and great, there's no error, there's no warning, everything is fine. So now we can simply do dot slash odts minus ts monitor. So it's a flag to show the monitor. So now we have to accept this. So what it looks like is, okay, this, there appears to be an overflow for the number of steps. So is there some issue? So it's int n steps. I wonder why there's an error in the number of steps. There appears to be some overflow happening over here. Oh. And okay, so this has to be TF because it's the final time. So let me recompile. Yeah, so the final time is 10. The number of steps is 45 and the error is this. Okay, fine. So everything looks quite okay. All right. So how do you actually go ahead and control this time stepping parameter? So what we can do is we can do the grep business that we had done earlier as well. So we can do dot slash odts and we can say help. So this help will return us a huge amount of information which we probably don't need. So out of this we will grep, so we'll pipe this output to the grep utility of Linux and we will say show me options which have the prefix ts. So these are the options. So we can say ts view binary, ts view draw. So let me launch xming so we can see how it looks. So let's do that. Let's see. So minus ts view draw. Is there some draw delay? Let me execute it and see. Okay, there was something. Minus draw pause underscore pause. Let's put a pause of 5 seconds. Oops. Hmm. So ts view solution. Let us. Yeah. So that's how the ODE goes up until t equal to 10. So let's have a look again. Okay. So let us do ts monitor solution. So it tells you what the value of the solution is at the final time. Okay. Or you could ideally do, so we can turn off the adaptive time stepping. So you can note over here that the time step is sort of dt, but the time step is kept adaptive, and the reason why time step is kept adaptive because the Runge-Kutta method really runs well with adaptive time stepping. So whenever it has a smooth function, it can take large steps. Whenever we have a fast varying function, we can always choose small steps. So now we can turn off time stepping, adaptive time stepping, and ask it to do um, time steps which are fixed. But have we defined some? Yeah. So if when time adaptive time stepping is not used, it will fall back on this default time stepping of 0.1. So we can do minus ts adapt type none minus ts monitor. So look, it's gonna take all the time steps like this. 3 10 to the, so why is it not giving me, yeah, okay. So let me recompile. So the error is 3.664 10 to the power minus 4. It took less steps. It gave us a fine error. Okay, so you can also change the tolerances that you choose in the error. So this particular error is based on a tolerance of 10 to the power minus 4, that is the default value, but we can change that particular tolerance as well. So we can say minus ts r tol 1.0 e minus 6 minus ts monitor. We can also change this. So the numerical error actually keeps on accumulating each step, but each step you are actually accruing a very small error. I mean, this is quite common for all time stepping methods. But yeah, I mean, this kind of thing keeps on happening, and one should not be too surprised. But the fact that you can modify the time step, you can choose the time step that you want, you can choose the dt to be 1.0 e minus 5. And you have to turn off the adaptive as well. So it will take more time, but it will give you a really accurate solution. But probably it's a bit too small, so let me cancel execution. Let me make it 10 to the power minus 2. So you get a very small error. So it's all a matter of how small or how large you choose the errors to be. In fact, if you choose this to be minus 12, the error keeps on accumulating because the delta t is quite large. So you can actually set a maximum delta, maximum dt. There's an option to change it. You can find it easily in the function reference. Okay, so this is how you can go about doing simple ODE integration with the help of uh, PETSc. In fact, let me just show you one last option which will be quite useful. So this will be TS type. So TS type can be Crank Nicholson, maybe no, or Runge-Kutta. So TS type Rk minus TS Rk type 2a. So let's see. So that's the second order. So there's a whole host of errors which you can easily obtain using this command, and unfortunately my scrolling does not seem to work, but you can scroll up and see all the different options that are available to you. So with this simple example, I'm gonna end this particular lecture, and you can um, take a look into your textbooks. You can solve a host of ordinary differential equations using PETSc just to get confidence with whether everything works properly or not. So with this, I end this particular lecture, and I'll see you next time. Bye.